The universe is not just expanding, it's accelerating, tearing itself apart faster and faster with every passing moment, driven by a mysterious force that makes up nearly 70% of everything that exists, yet we have absolutely no idea what it is. This is dark energy, the strangest discovery in the history of cosmology, and it's rewriting everything we thought we knew about the fate of the universe. Welcome to the most mind-bending cosmic mystery of our time, where the very fabric of space itself is pushing galaxies away from each other at ever-increasing speeds, and where the future holds something far more bizarre than anyone ever imagined. Let's rewind to 1998, a year that changed cosmology forever. Two independent teams of astronomers were studying distant supernovae, using these stellar explosions as cosmic mile markers to measure how the expansion of the universe was slowing down over time. You see, everyone expected gravity to be gradually slowing the expansion that began with the Big Bang, like a ball thrown into the air that eventually slows due to Earth's gravity. But when the results came in, the astronomers couldn't believe their eyes. The universe wasn't slowing down at all. It was speeding up. Distant supernovae were farther away than they should have been, meaning the universe had been expanding slower in the past and was now accelerating. This discovery was so unexpected, so contrary to everything physicists believed, that both teams checked and rechecked their data for months, certain they'd made a mistake. But the data was solid, and the implications were staggering. So what could possibly be pushing the universe apart against the inward pull of gravity? Scientists named this mysterious force dark energy, not because we understand what it is, but because we literally have no idea what it is beyond the fact that it exists, and it's causing cosmic acceleration. The name dark energy is really just a placeholder for our ignorance, a label we've given to one of the universe's deepest mysteries. And here's what makes it even more remarkable. Dark energy doesn't just exist in small amounts. Current measurements indicate that dark energy comprises about 68% of all the energy and matter in the universe. Regular matter, everything we can see and touch, all the stars, planets, gas, and dust, makes up less than 5%. Dark matter accounts for about 27%. This means that dark energy is the dominant component of the cosmos, and we're utterly clueless about its true nature. The leading theory about what dark energy might be takes us back to Albert Einstein and a modification he made to his equations of general relativity. When Einstein first developed his theory, he added something called the cosmological constant, essentially a property of space itself that creates a repulsive force. Einstein introduced this because he believed the universe was static, neither expanding nor contracting, and needed this repulsive force to counterbalance gravity. When astronomer Edwin Hubble later discovered that the universe was indeed expanding, Einstein reportedly called the cosmological constant his biggest blunder and removed it from his equations. But here's the cosmic irony. Einstein's supposed mistake might actually be the correct explanation for dark energy. If empty space possesses some inherent energy, what physicists call vacuum energy, then this would create exactly the kind of repulsive effect we observe. As the universe expands and more space comes into existence, more of this vacuum energy appears, driving ever faster expansion. It's as if the vacuum of space isn't truly empty, but filled with an invisible energy that pushes outward against gravity's inward pull. But if dark energy is vacuum energy, we run into a massive problem, literally one of the biggest problems in physics. When quantum physicists calculate how much vacuum energy should exist based on quantum field theory, they get a number that's 10 to the power of 120 times larger than what we actually observe. That's not just a little bit off, that's spectacularly, embarrassingly wrong, the worst theoretical prediction in the history of science. This enormous discrepancy tells us that either our understanding of quantum mechanics is fundamentally flawed, or there's some unknown mechanism that cancels out almost all of the vacuum energy, or dark energy is something else entirely that we haven't even conceived of yet. Some physicists have proposed alternative explanations, suggesting dark energy might be a new kind of energy field that varies over time, something they call quintessence after the classical fifth element. Others wonder if our theory of gravity itself needs modification on cosmic scales. But so far, the simple cosmological constant remains the best fit to observations, even though we can't explain why it has the value it does. The discovery of dark energy has profound implications for the ultimate fate of the universe. Before 1998, cosmologists debated between two possible futures. If there was enough matter in the universe, gravity would eventually halt the expansion and pull everything back together in a big crunch, the opposite of the Big Bang. If there wasn't enough matter, the universe would expand forever. but the expansion would gradually slow down as gravity's influence, though never enough to reverse the expansion, would at least decelerate it. Dark energy has introduced a third possibility, and it's the one that appears to be our universe's destiny, the Big Rip, or endless acceleration. As dark energy continues to drive accelerating expansion, galaxies will move apart ever faster. Eventually, billions of years from now, distant galaxies will recede from us faster than the speed of light. This doesn't violate relativity because it's space itself that's expanding, carrying galaxies along with it. These galaxies won't disappear instantly, but will fade from view as their light gets redshifted to wavelengths we can't detect. Looking even further into the future, the universe becomes a lonely place. After a few 100 billion years, galaxies outside our local group, the cluster of galaxies gravitationally bound together, including the Milky Way and Andromeda, will have moved beyond the cosmic horizon. Future astronomers born in that distant era, if they exist, will observe a universe containing only their local galaxy and empty darkness beyond. They'll have no evidence that other galaxies exist or ever existed. No evidence of the Big Bang. No cosmic microwave background radiation. Their universe will appear static and eternal, and they'll have no way to discover the rich cosmic history we can observe today. In a sense, we live in a privileged time, able to see deep into space, and therefore back in time, able to study the universe's evolution and the evidence of its explosive beginning.
But dark energy might have even more dramatic effects if its strength increases over time. Some theoretical models suggest that dark energy could grow stronger as the universe ages, eventually becoming so powerful that it doesn't just push galaxies apart but tears apart galaxy clusters, then individual galaxies, then solar systems, then planets, and ultimately atoms themselves in what's called the Big Rip. In this scenario, the fabric of space would be stretching so rapidly that even the electromagnetic and nuclear forces holding matter together couldn't overcome it. The universe would end not in fire or ice but in complete disintegration, everything shredded apart as space itself expands faster than the speed of light. Current observations suggest this isn't our fate, that dark energy appears to be a cosmological constant with unchanging strength. But we can't rule out more exotic possibilities with observations spanning only a few decades of a universe that's 13.8 billion years old. Studying dark energy has become one of the highest priorities in modern cosmology, and astronomers are deploying increasingly sophisticated tools to probe its properties. Projects like the Dark Energy Survey and the upcoming Vera Rubin Observatory are mapping millions of galaxies and measuring subtle effects like weak gravitational lensing, where dark energy influences how the universe's matter distribution bends light from distant sources. Space telescopes like the recently launched Euclid mission are designed specifically to measure the geometry and expansion history of the universe with unprecedented precision. By observing how cosmic structures formed and evolved over billions of years, these projects aim to determine whether dark energy is truly constant or changing over time, which would profoundly impact our understanding of fundamental physics. One of the most fascinating aspects of dark energy research is how it connects to some of the deepest questions in phys.